Let's look at the details of conduction heat transfer. And for this mode of heat transfer, we are preliminarily looking at solids. And so conduction is referred to the transfer of heat by molecular or atomic interaction. Now, in solids, molecules have a fixed position, and they can transfer heat or energy, thermal energy by two forms. So let's say if I'm looking at a solid, let's say these are solid molecules. These solid molecules have fixed positions and they are connected by lattices. Now, if one side of these solids get exposed to a higher temperature, so let's say here is high temperature versus here that is low temperature, now heat can flow through these solids through the lattice vibration. And it can also flow through electron motion. So as one side of that exposed to the higher heat, or there is a temperature gradient, these lattices start to vibrate and transfer heat, and at the same time electrons can transfer heat. Now one thing here is some solid could show only one way of like transferring heats by conduction. So we have two class of solids, non-conductor, that only transfer thermal energy by lattice vibration. And the other ones that are good conductors are the ones, good conductors, both conduction modes exist. So in conductors, heat can be transferred by both effects, electron motions and lattice vibration. Generally speaking, good electrical conductors are generally, is not always the case, are generally good heat conductors. Let's say we have a solid slab and one side of the solid slab is exposed to a higher temperature, so I'm just going to call it T1, and the other one is at a lower temperature. And we know that heat is flowing from the high temperature to the low temperature. Now, what is the rate of heat transfer? Heat flux, or rate of heat flow per unit area, as we show by the Q double prime called Q over A, is going to be proportional to this temperature gradient that exists in this solid. Now, if we use a proportionality constant, what we are going to get here is Q is going to be Ka dt over dx. And this is what we call Fourier's law of heat conduction. In this equation, Q is the rate of heat flow, and it has a unit of joule per second or watt. We have area, we have dt dx, and we have K. A is surface area, normal to heat flow. So for this example, if we have, let's say we have this solid slab or solid wall, okay? This is gonna be the area that is normal to the heat flow that's passing through this solid. Now dt dx is the temperature gradient. In the direction of heat flow. And it has a unit of Kelvin per meter. Surface area has a unit of meter square, and K is what we refer as thermal conductivity, which has a unit of watt per meter Kelvin. There is a missing point here. We have a negative sign. Q is minus Ka dt dx. And we need this minus sign. The minus sign is necessary because the heat is flowing in the direction of negative gradient from the higher temperature to the lower temperature. So in order to get a positive heat flow rate, we would need this negative sign to be appear here. Now that we are talking about thermal conductivity, let me give you a little bit of detail about that. Thermal conductivity. First of all, thermal conductivity is the property of the medium, and it indicates how easy heat flows through the medium by conduction. And let's say for the above examples, if I write the Fourier law of heat conduction, Q to minus Ka dt dx for similar area and temperature gradient, what we can see from this equation here is that Q is large if K is large. Or in the other word, what we can say here is that in medium, now so if a medium has a large thermal conductivity, it allows a higher rate of heat flow by conduction, or what we refer to as that medium that solid or that material as to be good conductor or poor insulator. On the other hand, Q is small if K is small. Or similarly, what I can write here is a medium that has a small k will allow a smaller or a lower rate of heat flow by conduction, and that's what we refer as poor conductor or good insulator. Now, in terms of the values, let's have a couple of examples for the values. For example, what we have for pure silver, thermal conductivity of pure silver is about 410 watt per meter per Kelvin. This is at 0 degrees centigrade. And for glass wool, for example, same temperature, K, I believe, is 4 order of magnitude smaller, watt per meter Kelvin at 0 degrees C. And remember, you see, like there is a huge change between being a very good conductor to be a very good insulator here. And the last point that I want to mention that we will probably discuss later is K is temperature dependent. Now, for the sake of this class, in most examples, we will assume K is constant unless that I specify that one.